Welcome back to part 2 of this chapter. So chemical shifts are often considered as empirical quantities that escape any sort of attempt to explain them. But of course that's not true. People, and chemists in particular, physicists as well, would like to give an explanation. And there are in fact a wide variety of explanations. Some of them are conflicting, sometimes they make sense, sometimes they don't, and one has to be very careful to pick one's way among this minefield of explanations. But let me give you some of the elements so that you can judge yourself how sound this science is. So here we have Pauling's electronegativity. We all know that there is a series from iodine to bromine to chlorine to fluor where the electronegativity increases, that is to say, the electron withdrawing ability. And it turns out that if we take methyl halides, CH3X, where X is one of the above, then it turns out that the chemical shift of the protons of the methyl group follows a particular trend, which is roughly linear with the Pauling definition of electronegativity. So you might say the stronger the withdrawal, the larger the chemical shift of the proton that is attached to the methyl group that is neighboring to the halide. So far, so good. This makes sense. I wouldn't use it as a way of determining the electronegativity, but you could if you wished. Now it turns out that the electronegativity has an effect beyond the neighboring methyl group. In fact, if we take a chlorine at the end of a long chain, so this is now one of these halides at the end of a butane molecule, you can see that the protons on the neighboring methylene group are shifted all the way to the left, but the second one is affected much less, the third one is hardly affected at all, and the methyl group is so far away that it has essentially the same chemical shift as the methyl group in a simple propane molecule. So this tells you something about the range of this electronegative electron withdrawing effect. There is an important aspect when one tries to rationalize chemical shifts, that sometimes they go hand in hand with the chemist's perception of how the molecule really looks like. And when I say the chemist's perception, I mean the so-called resonance structure. Take this simple aromatic molecule, and we know that the NO2 group is an electron withdrawing group. And the organic chemist rationalizes this by saying that some small fraction of this is not in fact as drawn here, but that the double bond migrates to the single bond and becomes therefore a double bond. And concomitantly, there is a positive charge that appears here on the neighboring carbon. And you can do this one more step. You can cause this double bond to migrate here, and then the positive charge appears in para position with respect to the NO2 minus group. Well, these structures are known as resonance structures, and they're very familiar to organic chemists because they allow one to rationalize reactivity. Where do certain substituents go, and questions like that. And in fact, these pictures have been developed hand in hand with the observation of the proton chemical shifts. And you see an example here. So nitrobenzene, which is these three molecules here, actually there are three different chemical shifts. There's one that is strongly deshielded with respect to benzene. That is the one in the ortho position. You can imagine that because the electrons are being withdrawn, there is a lack of an electron cloud, and therefore it's less shielded. And likewise, in the para position, that is over here, there's a similar effect, although it's much less pronounced. It's a bit paradoxical because in the resonance structures, there's really no need to say that the ortho plus is dominant over the para plus, but you see that at least empirically it turns out that the effect is most pronounced for the ortho and very little for the para. Meanwhile, according to this argument, the proton in the meta position, that's this one here, should not be affected at all. Well, it is also affected somewhat with respect to benzene, but apparently that's a different effect than the resonance effect. Now, the beauty of this argument is that it's exactly opposite to what you see in aniline. In aniline, we have an electron-donating group, so we have the lone pair on the nitrogen here, and this lone pair can go here, and then this double bond will move into an into this position so that we have an excess charge here. And in the second step, we can decide to put that charge here and put this one over here so that we now have an excess charge in the para position. And consequently, you expect the ortho position to be shielded because there's more electrons than there were before you delocalize them, and therefore it goes towards the right. And the para position would be somewhat less shielded, and the meta position should not be shielded at all, but nevertheless it is somewhat shielded. You notice that it's not exactly symmetrical. For example, the para is very close to the ortho here, where that's not the case on the left side. So that shows that these arguments are essentially qualitative and that you should not give them the status of a serious theory, just more to guide the intuition. But chemistry is a great deal about intuition, so there's nothing wrong with using that type of thinking. Here we have an example of carbon-13 chemical shifts of paracarbons in substituted benzenes. So with reference to these molecules, we're talking now about the carbon, not the proton, the carbon that is in para position with respect to the substituent. And now we vary the substituent. So we can put this NH2 here, which is like here, the amine, or we can put the NO2 like here, the nitro group. But there are all sorts of things in between. And we can use this chemical shift scale here as a measure of the ability of these substituents to donate electrons into the phenyl group or to withdraw them from the same aromatic ring. So this is a very nice way of classifying the electronegativity of those groups, and also to predict the reactivity, which of course is essential in chemistry. Here is a more exotic example. In fact, this was published many years ago by Ray Freeman, Murray and Richards. Ray Freeman was my PhD advisor and Rex Richards was his advisor. So in a way, he is my intellectual grandfather, if I dare say so. And I vividly recommend you to look up this publication in the Proceedings of the Royal Society. It's quite a few years ago, but nevertheless of great current interest. Now, what these people did, they knew that cobalt complexes, for example here, with the nitrile group or the ethylene diamine or the ammonium and all the others, that they have different colors and different optical transitions. And these optical transitions are due to the transition, the crystal field splitting between the so-called T2G orbitals and the EG orbitals in the cobalt complex, which is in these cases is always in a hexagonal environment. And what they found is they started measuring cobalt-58 chemical shifts, something that is not at all common in the literature, but clearly a heroic attempt to discover a new correlation. And they found a wonderful correlation between the chemical shift of the cobalt and the wavelength in nanometers of the optical transition. So this is somewhere in the visible, UV visible light. Then they said, aha, well, this is something to do with this is a contribution to the chemical shift, which they attributed to what was now known as a paramagnetic contribution to the shift. They noticed that it's inversely proportional to the parameter delta, which is simply the splitting, the transition frequency of the optical transition, and they also considered that it should be relevant to include an average over R3, where R3 is basically the radius of the size of the electron cloud that is responsible for the chemical shift. Now, this is really beautiful observation, very interesting, very stimulating, but unfortunately there are not many molecules that behave in such a clear way, not many examples of this effect. Now, in the meantime, people have been trying to split contributions to nuclear shielding into different parameters. The effect that I spoke about at the very beginning of chapter 2, the one that we find in helium-3 and in xenon-129, which, by the way, is also known as the lamp shift, is more properly known as a diamagnetic shielding. So in diamagnetic shielding, the induced magnetic field, induced by the circulation of the electrons, is anti-parallel to the external field. But we also have situations where the shielding is paramagnetic. In that case, there is a local field which is actually parallel to the external field and therefore adds up to the external field. Then there are effects which are due to remote groups or remote currents or currents in remote groups, and of course other sources. Now, it's very nice to make a list of these, but it's very difficult in practice to split an observed chemical shift into separate contributions. Now, to remember here that the magnitudes of induced diamagnetic and paramagnetic currents can be related to local electron densities and to electronic excitation energies. So this is clearly inspired by the work of Ray Freeman and Rex Richards on cobalt, but is not necessarily of universal application. Some of the most important contributions to chemical shifts are so-called ring current effects, which are specific to aromatic compounds. You see in the scheme here, this ring here is supposed to represent a benzene ring, or in fact any aromatic ring. You see that the induced field induced by the electrons that circulate in this ring is opposite to the external field. And if we could have a proton right in the center of the benzene ring, it would be shielded because it experiences a field that is smaller than the external field. But in fact, protons in benzene rings, as you know, are on the outside of the ring. And therefore, they experience a local magnetic field, an induced field, which adds to the external field. And the result of that is that they appear de-shielded. Now, one way of measuring this effect is comparing benzene, where the chemical shift is about 7.3 ppm with respect to TMS, with a form here where one of the three double bonds has been reduced by addition of a hydrogen molecule, and consequently there is no possibility for these electrons to run around the circle, and they cannot sustain a ring current and therefore not induce a magnetic dipole that is opposite to the external dipole. Where you see immediately that the chemical shift of this proton goes from 7.3 to 5.9, so it has become shielded or less de-shielded if you prefer. A more spectacular example here, this molecule is a rather contrived piece of chemistry. It was made in the days that people were trying to find extremes of the most de-shielded or the most shielded compound, and the most important part of it is that this methyl group here is just above the aromatic ring. This is an aromatic ring, and the methyl group is just above that ring. And it turns out that it's not just a bit shielded, but it is more shielded than tetramethylsilane, so it has a negative value, if you wish. It is to the right of TMS in an ordinary proton spectrum plotted on the usual scale. At the same time, all the protons, the aromatic protons which you find here, and there are quite a few of them, they are in this range, that is to say, they are very far to the left of the spectrum or strongly de-shielded. Perhaps a cleaner illustration of this comes from this aniline, which has slow interconversion of internal and external protons through reorientation. But the basic thing is that because the protons are on the inside of the ring where the current is circulating, they have a negative value of the chemical shift, delta, which means that they are on the right-hand side compared to TMS, whereas the other ones here are just like in benzene. They are they're de-shielded, and therefore on the left of the spectrum. You notice that one goes from 7.3 to 8.5 or so to 9.28, so this goes more and more pronounced. Now, there are also interesting things that happen if we have triple bonds and other exotic pieces of chemistry, but triple bonds are not exotic at all. In this case, we have to worry about something else, and that is about the orientation of the triple bond with respect to the external field. And this, in fact, introduces a property of chemical shifts which is very important when we do solid-state NMR, and that is the chemical shift depends on the orientation of the molecule with respect to the external field. And it turns out that, somewhat against intuition as far as mine is concerned, if the triple bond is perpendicular to the external field, then there are strong currents within this conjugated pi electron system, and the net effect of that is a paramagnetic shift where there is a strong dipole which is parallel to the external field. and therefore we have these arrows here representing the flux, and you can see that they will affect, for example, the protons, the acetylenic protons here and here, where they have a situation which is actually opposite to what happens in, for example, benzene. But the situation is compounded by the fact that if the complexity is compounded by the fact that if the triple bond is parallel to the field, then we have to draw it this way. It turns out that these electrons circulate less freely in this situation, and therefore the induced paramagnetic dipole is weaker. If the dipole were equal here and here, and if one then invokes isotropic tumbling of the molecule so that it can adopt all possible orientations in space, then there would be no net effect. But there is an imbalance, you see. Here the paramagnetic induced dipole is strong and here it is weak, and therefore there is no averaging when it tumbles over all possible positions. This has curious effects. For example, if we take a famous series, so this is just ethane, CH3, CH3. It is not very far from methane, and it's on the right-hand side, be close to 1 ppm. If we now introduce a double bond, we jump from here to here, and if we introduce a triple bond, you might think that we go even further. Well, that's not true. In fact, we go back one step, so to speak, and that is because of the anisotropy of the triple bond, of the electron motion within the triple bond. Such things can be represented in terms of regions of shielding and deshielding, so we can distinguish such cases where the dipole, the paramagnetic dipole for the parallel position is larger than the dipole for the perpendicular position, in which case we get a distribution of fields like this, or the opposite case where, of course, we have opposite signs. Notice that these are drawn on these cones, and in fact these cones are schematic representations of tensors, and they look a bit like orbitals, and you may notice that the angle subtended by these cones is this angle here. We shall refer to that as the magic angle, and in fact it's about 54 degrees, and we shall see that if we somehow orient our molecules in a solid along that line, we get a simplified spectrum. That is also the basis of magic angle spinning. Now there are some implications of these neighboring groups. We spoke about acetylene, and we spoke about the proton which is attached, the acetylenic proton, but more spectacular effects occur in molecules such as this. So this is the simple phenanthine, where this aromatic proton resonates at about 8 and something ppm, but here it is sort of squeezed very close to the triple bond, and you see it has a massive effect of nearly 2 ppm. Further deshielded because of the anisotropy of the neighboring group. This is now the neighboring group, and it has an effect on the chemical shift, which of course does not occur if the triple bond is absent. So this is deshielding due to magnetic anisotropy. Now there are some things which are perhaps more important to the chemist, and here we see a case of deshielding due to hydrogen bonding. Hydrogen bonding, of course, is essential in chemistry and also in biology. Remember that if we think of double-stranded DNA, the two strands are held together by very, very weak interactions called hydrogen bonds. It is only because there are so many of them that these two strands hold together. So characterizing hydrogen bonds is actually quite important in chemistry. And here we see an example, or two examples actually. We see that the proton here, which is sort of sharing its attention between two oxygens, I'm not saying it's symmetrically distributed, there's a proper bond to this oxygen and a weaker bond to that oxygen, but you see that the electron cloud is very weakened, very diminished around that hydrogen, and therefore it is very much deshielded. In fact, its chemical shift is 11 and something ppm. A more simple example here, we see that this hydrogen really doesn't know where it wants to go, because the whole molecule can be redrawn, the double bonds can hop around, and the net effect is that this hydrogen is almost bare. There are almost no electrons to shield it, and therefore it turns out very heavily deshielded, because there are no electrons to shield it, and that of course is characteristic of such hydrogen bonds. And as I said, we find similar things in DNA, deoxyribonucleic acids, and also in RNAs, which are very popular today to study by bio-NMR. Now there is another picture which I think is very instructive, and I must say that Peter Hoare did a tremendous job in selecting good examples, and this is the one of ethanol. Now ethanol we all know, and some of this know it too well, which I can write like this, and I give it a little bend, because next to it I shall be drawing another ethanol molecule, very similar structure but just drawn head to tail, and this is known as an ethanol dimer, and it turns out that the dimer holds together with these two hydrogen bonds. And because there are these intermolecular hydrogen bonds, the electron density around each of these two hydrogens is very weak, very diminished, and we are in effect in a position similar to this, and so the chemical shift of that hydrogen is very much to the left, or it's very de-shielded. Well, that's why in ordinary ethanol, if we have 1 molar ethanol in a aprotic solvent such as tetrachlorocarbon, then we have the OH, which is, as you can see, appears about near 5 and something ppm. But as we dilute the ethanol to 1/10 of a mole per liter to 100 to 1,000, we see that the OH resonance moves to the right. And that is because as we dilute, we can break up this dimer so that it falls apart into monomers, and because the solvent here, the aprotic solvent, is unable of making any hydrogen bonds with either of these monomers, the hydrogen is less deplenished, or its environment is less depleted of electrons, and therefore it's more shielded, and as you can see, it moves towards lower ppm values, lower chemical shifts. Now you will notice that this is not an experimental spectrum. In fact, there's no reference given to it either in the book, and the reason is that it's not so easy to observe this hydrogen, because the hydrogen will also exchange by chemical exchange, and therefore the very least that can happen is that it would be very broad, and sometimes it is also at a different chemical shift that depends on the entire structure. But it's an interesting principle, and the demonstration is very nicely done. Now let me take you to one of the last examples, and this is unpaired electrons. There are lots and lots of systems in organic chemistry where we have free electrons or unpaired electrons. In organic chemistry we call them radicals. In metals we don't call them radicals, simply they have electrons that are not paired up in pairs in individual orbitals. Iron is a good example of an atom, of a metal, that often has unpaired electrons. Zinc, on the other hand, has an even number of electrons that are nicely paired up. So what you see here is a complex or spectra. These are proton NMR spectra of complexes such as this, where the 4 nitrogens hold the metal ion in the middle, and this metal can be either zinc or iron. And what we actually observe is the chemical shifts of this HX here and of the HY. As you go around the ring, you will see that there are really only 2 chemical shifts. They alternate, so there's 2 HXs and HY, 2 HXs, etc. But that's not important here. The important part is that if we have zinc in the center, then it's not paramagnetic. There are no free electrons. And we have a simple case where all these are aromatic protons, and they resonate somewhere between 8 and 9 ppm, which is fine, nothing abnormal. But if we replace the zinc by iron 2, I believe it's in this case, then we see tremendous change. They are dramatically shielded, one could say, or shifted towards the right-hand side in this scale, and X and Y are no longer similar. Their degeneracy, the near degeneracy that we had in the zinc case, is now lifted. Now this is due to the coupling between the free electrons and these protons. This is due to the coupling between the free electrons and the protons, a long-range coupling, which in fact is known as hyperfine coupling, and which leads to a shift because the distribution of the polarization between alpha and beta states for an electron is not 50-50, but it's displaced towards the lowest energy state following the Boltzmann rule. And in fact, it's the rapid transitions between electrons in the alpha and the beta state which give rise to an average chemical shift, if you will, or an average position of the proton lines which depend on the environment. So, to conclude this second chapter of Peter Hoare's little book, let's look at the summary that the author has put together at the end of the chapter. First of all, we notice that nuclei, such as protons, are embedded in molecules and that they may have slightly different NMR frequencies depending on the environment, an effect that is known as the chemical shift. Such effects occur not only for protons but also for carbon-13, nitrogen-15, phosphorus-31, and depending on the sort of system that we're looking at, silicon-29 and many other nuclei in the periodic table. Chemical shifts arise from induced electronic currents, which can either shield or de-shield the nuclei from the applied magnetic field. The chemical shift parameter delta is used to quantify the extent, the degree of nuclear shielding or de-shielding with respect to a conventional reference, sometimes tetramethylsilane for protons and carbon, and other nuclei have different standards, of course. So the magnitudes of induced diamagnetic and paramagnetic currents can be related to local electron densities and electronic excitation energies. Chemical shifts can often be understood by considering the effects of electron donating and electron withdrawing groups, by looking at the effects of induced currents in neighboring groups, such as triple bonds or aromatic rings, looking at charged or polar groups, at the role of hydrogen bonds and of unpaired electrons, which have hyperfine couplings to the nuclei that we are looking at. Chemical shifts distinguish nuclei in different environments in molecules and therefore give information both on the molecular identity and on the molecular structure.